Hello, everyone. I hope my volume is fine. You hear me? Okay. Today's session is on optimization of economic functions. Okay. In chapter 5, we found that the turning point of a nonlinear function to be where the derivative of the equation is 0. Yeah, so where the slope was zero. And furthermore, the nature of such turning point is determined where the second derivative is say, okay, where if the second derivative is greater than 0, like f prime of x was greater than 0, then we say that turning point, it is a minimum point. If it's greater than 0, it is a minimum point. And then if f prime, the second derivative, is less than 0, then it is a maximum point. Okay, first, we said the turning points of a nonlinear function are where the derivative of that given function, that nonlinear function, is 0, right? And then we said the nature of them. If the second derivative of that given function is greater than 0, then that turning point, it is a minimum point. And again, if the second derivative of that point, of that x value, if it is less than 0, then we said that is a maximum point, a stationary point, or the turning point. Okay, now we want to apply that in economic functions, like in total revenue, total cost, and profit. We want to apply this on the economics functions, like the total revenue, the total cost, and the profit. Although the optimal decision differs from company to company, the objective of optimization technique is to obtain a condition under the marginal revenue is equal to the marginal cost, right? And again, profit is maximized at a level of output when the marginal revenue is equal to the marginal cost. Okay. And another thing that you need to know is that the marginal cost is the change in the total cost resulting from one unit change of outputs, and the marginal revenue is the change in total revenue resulting from one change in sale. Okay. For example, give me a second. Okay, for example, suppose the demand and the total cost function are given as follows. Okay, this is EG1. Suppose we are given the demand as P equals to 5504 minus 0.8 Q, and total cost given as 608,508 plus 120 Q, right? Let's say you are given these two and you are asked to determine the price and quantity for which profit is maximized using the differentiation as well as the marginal revenue and the marginal cost. Okay, let me repeat this. You are given a demand function, which is this, and also a total cost function, which is this, right? And you are asked to determine the price and quantity for which the profit is maximized using the differentiation as well as the marginal revenue and marginal cost. Okay. From the previous chapter, we know that the marginal revenue is the derivative of the total revenue, okay? The derivative of the total revenue. And again, we know that the marginal cost is the derivative of the total revenue, of the total cost, okay? From previous chapter, we know these two conditions. The marginal revenue is the derivative of the total revenue, and the marginal cost is the derivative of the total cost. Okay. Here, remember, they said determine the price and quantity for which profit is maximized, right? And we know that profits, the profit is equal to the total revenue minus the total cost. Okay, we know these two, right? So, okay, remember we are given the total cost, right? So for us to use this equation, because we are asked to determine the price and quantity for which the profit is maximized. And they said they gave us a hint that we should use differentiation as well as the marginal revenue and the marginal cost. Yes. Okay. And remember, I said when I was starting, I gave you, on the few statements that I mentioned, I said profit is maximized at the level of outputs when the marginal revenue is equal to the marginal cost, right? Profit is at max when marginal revenue equals to the marginal cost. Okay. Remember, they said we should use differentiation and then we use the marginal revenue as well as the marginal cost. Okay. And we know that we said from the previous session, the marginal revenue is the derivative of the total revenue, right? And the marginal cost is the derivative of the total cost. So if we can find the marginal revenue and the total cost and equate them, that means and equate them and solve for the price and the quantity, or we solve for the quantity and use that quantity to find the total profit, the profits, the maximized profit. Okay, right. Let's start by using this condition, this one. This condition says the marginal revenue is equal to the derivative of the total revenue. The total revenue. But we don't know what is the total revenue, right? So we need to find the total revenue before we use this condition. But we are given, remember, we are given the demand function, this. And from this, we can use the demand function to find the total revenue. Because remember, This is the formula for finding the total revenue if you are given the demand. It would be total revenue equals to the demand function times the quantity demanded, the units of the quantity demanded. And our demand function is given as 5504 minus 0.8 Q. Okay, and then times this demand function. And if you simplify this, we'll have 5504 Q minus 0.8 Q squared. And this is the total revenue, right? But remember, the reason we went this way to find the total revenue is because we wanted to differentiate the total revenue to find the marginal revenue. Since we now know the total revenue function, we can differentiate it to find the marginal revenue. And we said the marginal revenue is equal to the derivative of the total revenue, which is 5504 Q minus 0.8 Q squared, right? To differentiate this, okay, we can put it like this. We can first separate it, 0.4 d over dq of q minus 0.8. Again, we are using the rules of derivative. Different d over dq of q squared. Okay, if we differentiate these, we'll have something like this. We'll have 5504, because here we'll have 1, right? We'll have 1 because the derivative of q is 1. Then we have minus 0.2 times the derivative of q squared is 2q. This is 0.8, it's 2q. Okay, if you simplify this will be 5504. This times this minus 1.6q, and this is your marginal revenue, right? This is your marginal revenue. Okay, remember the reason we were finding the marginal revenue. They said we should use the marginal revenue and the marginal cost. So the next step is to find the marginal cost. And remember, okay, we have the marginal revenue. Remember, we said the marginal cost from the previous function is equal to the derivative of the total cost. And we were given the total cost as 608,508 plus 120q. Okay, and if we differentiate this, we'll have something like this. The derivative of 60850, right, plus 120 times the derivative of q, right? If we differentiate this is a constant, and we know that from our rules of derivative, the derivative rules, derivation rules, the derivative of constant is 0. So here we'll find 0 if you differentiate. Then if you differentiate q, the derivative of q is 1. So this means we have 120 times q, which is 120, and this is our marginal cost, right? And then we go back to this condition. P is at maximum when the marginal revenue is equal to the marginal cost. Remember, they said determine the price and quantity for which profit is maximized. So this means we want the price and the profit when the profit is at maximum. Okay. And we said the profit is at maximum when the marginal revenue is equal to the marginal cost. So the next step is to equate these two. Marginal revenue equals to the marginal cost, right? Okay, and we said the marginal revenue is equal to, this is what we obtained, 5504 minus 1,6 Q equals to, for a marginal cost, we obtain 120, right? So the next step is to simplify, is to try and solve for the quantity. If it's, okay, to solve for the quantity, I'm gonna transpose this side. If I do that, I'll have minus 1,6 Q equals to 120 minus 5504. And this gives me minus 1,6 Q equals to minus 5384, right? But I'm not looking for minus 1,6 Q. I just want Q, right? So I can divide it with minus 1,6 on both sides, minus 1,6. And this will give you Q equals to 33665, right? And this is your quantity when the profit is maximized. Okay, and then we know that the profits, is equal to total revenue minus okay. Remember, we were given a demand function as P equals 5504 minus 0,8 Q. And since this is the quantity when the profit is maximized, so we can just substitute it here and solve for P and solve for the price. Okay, since this is the quantity when when the profit is maximized, this means the corresponding value of Q or of P when the quantity is this, that would be the price when the profit is maximized. So the next step, I'll just take this and substitute back here. If I do that, I will have 5504 minus 0,8 times 3365, right? And if you punch this in your calculator, you should obtain 2812. And this is the price of your quantity when the profit is at maximized. Okay. Remember, they gave us a hint to use the marginal revenue and the marginal cost, and we did use it. This is what we obtained. And again, they said we should use the derivation, and that's what we used here and also here. Okay, let's try and do another example. Yeah, but we're still going to have a total session. I'm still going to have total session, but let me try and do more examples. Okay, example 2. Okay, suppose now you are given a demand function for any goods as P equals to 200 minus 3Q. Okay, this is your demand function. Here, P, this represents the price. It's the price per unit. And Q is the number of units produced and sold. Okay, then the question is, from the demand function, find a total revenue using this demand function. Okay. Okay, what can we find from here using this demand function? Okay, we can find the total revenue, because we know that the total revenue is equal to price per unit. Price per unit and times the number of units produced or sold of units. Okay. Remember, I said we are given a demand function whereby P represents price per unit and Q represents the number of units produced and sold. Okay. So if the total revenue is equals to this, then that means for a total revenue, we'll have 200 minus 3Q times Q. And this will give us 200Q minus 3Q squared. And this is the total revenue. What more can we find from here? We can find the marginal revenue if we have a total revenue. And we know that the marginal revenue is equal to the derivative of the total revenue. The derivative of the total revenue. And we said the total revenue is 200Q minus 3Q squared, right? Okay. And if we differentiate, do this derivative, we'll have 200 minus 6Q, and this is your marginal revenue. Okay. This means the total revenue has the derivative, has the turning point where the marginal revenue is zero. Remember, we said the turning points are the points whereby your given function, its derivative is zero. Let's say our given function is the total revenue. If the derivative of this total revenue is zero, then that means those are the turning point for the total revenue. If the derivative of the total revenue. And since the marginal revenue is the derivative of the total revenue, that means the turning points of the total revenue function would be when the marginal revenue is zero. Okay, let's try and do that. If we let the marginal revenue equals to zero, this means we have 200 minus 6Q equals to zero. If we solve for Q here, we'll have minus 6Q equals to minus 200. And this will give us, divide by minus 6, divide by minus 6, we'll have Q equals to 33.33. And this we can round off to 33, just 33. So this simply means the turning point of the total revenue function is where Q is equal to 33. But what is the nature of this Q, of this quantity? Is it the maximum point or the minimum point? Remember, we said to determine the nature of the turning point, we need to find the second derivative, right? From the previous session, we need to find the second derivative. And we said if the second derivative is less than zero means it is the maximum turning point or the maximum stationary point. If it's greater than zero, if the second derivative is greater than zero, that means we have a minimum point. Okay, let's find the second derivative. The first derivative is the marginal revenue. So to find the second derivative, we need to differentiate the marginal revenue, because remember, the marginal revenue is the first derivative of the total revenue. Okay, so the derivative of the marginal revenue would be, what is our marginal revenue? Our marginal revenue is 200 minus 6Q. Okay, we want to find the derivative of this. This represents the derivative. What do we get when you differentiate 200? You get 0, because 200 is a constant and the derivative of a constant is 0. What do we get when we differentiate minus 6Q? We get minus 6, right? Okay, so this means this is the second derivative of the total revenue. This means TR prime prime of Q, which is MR prime of Q. And since this is less than, okay, since this is equal to minus 6, and we know that minus 6 is less than 0, so we can conclude from here that when Q is equal to 33, we have a maximum turning point, right? So this means for us to make a total, to maximize the total revenue, we should produce and sell 33 units, right? But what would be the total revenue if we produce and sell this 33 units of products? Okay, you go back, that means you need to go back to the total revenue, and where there is the quantity, you substitute it with 33, and the equation for a total revenue is this. This was the total revenue. So where there is Q, substitute this with 33. So this means we'll have 200 times 33 minus 3 times 33 squared. And if you punch this in your calculator, this is what you should obtain. This is your maximized total revenue. This is how you will maximize your total revenue. Okay, first we were given the demand function, right? And then we were asked to find the total revenue, the maximized total revenue, right? And then we first differentiated the total revenue to find the marginal revenue, right? But to get the turning point, the stationary point of the total revenue, we let the marginal revenue to be 0, and then we solved for the quantity and we obtained 33, right? And then the next step was to find the nature of that 33. Find the second derivative, and the second derivative was negative, was less than 0. That means the point that we obtained, which is 33, is the maximum point, right? Then the next step was to find the exact value of the total revenue if the total revenue is maximized. Remember, we said it's at maximum on the turning points, right? And the turning point was at 33. So we just took the next step, take 33 and substitute where there is a total on your total revenue function. And after that, this is what we obtained. And we can conclude from here that this is the total revenue at maximum, the maximized total revenue. Okay. Let's do another example. Okay. Suppose This is example 3. Okay, this is example 3. Suppose you are given a demand function as P equals 30 minus 5 ln Q. Okay, this is your demand function, right? Suppose the question says, calculate the total revenue. The maximized total revenue, or maybe let's say the question says maximized the total revenue, or find the maximum total revenue. Okay, here we are given the demand function as 30 minus 5 ln Q, right? Remember, if you are given the demand function, then your total revenue will be the demand function times the quantity demanded, the units, the quantity demanded. Okay, and your demand function is 30 minus 5 ln Q, then times Q. And if you multiply this is what you'll obtain. 30 Q minus 5 ln Q minus Q minus 5 Q ln Q. Okay, this is what you'll obtain. And this is your total revenue, right? But they said we should find the total revenue at maximum or minimum, maximum or minimum, right? Okay, let's see what we can find. We need to find the turning point of the total revenue. To find the turning point of the total revenue, we need to differentiate the total revenue and equate the derivative to 0. But you know that when we differentiate the total revenue, we'll find the marginal revenue. And we know that the marginal revenue is the derivative of the total revenue. So this means we need to equate the marginal revenue to 0 to find the stationary point of the turning point of the total revenue. So we have dq of total revenue, right? So this means we have dq of 30q minus 5q ln q. And this would be 30 ln 30d over dq of q minus 5d over dq of q ln q, right? This, you see here, this is the product of two functions, meaning if we differentiate here, we'll have to use the product rule. Okay, let's find this derivative. What do we get if we differentiate q? The derivative of q is 1. So this means we'll have 30 times 1 minus 5. Okay, here, if we differentiate this, we'll have, okay, let's say we keep the second function, which is ln q. Then we differentiate the first function, which is q. We are using a product rule, so it's plus. We keep the first function, which is q, then we differentiate the second function, which is ln q, right? Differentiate the second function. And this will give us 30 times 1, it's 30 minus 5 times. We keep this ln q, we differentiate q. The derivative of q is 1. Plus, we keep this, which is q, we differentiate ln q. The derivative of ln q is 1 over q. So this means if we simplify this, we will have 30 minus 5 times ln q times 1 is ln q, plus Q times 1 over Q. Q and Q will cancel out and you'll have 1, right? And if you want to simplify this further, you'll have 30 minus 5 times ln Q minus 5 ln Q minus 5 times 1 minus 5. And then you collect the like terms. You have 30 minus 5. That will give you 25 minus 5 ln Q. And this is your marginal revenue, right? But we are not looking for the marginal revenue. We want to find Q, the quantity, the turning point, which is the turning point of the total revenue. And the turning point of the total revenue is when the marginal revenue is equal to 0. Okay. The turning point of the total revenue is when the marginal revenue is equal to 0, right? Okay, and this is our marginal revenue. So this means we have 25 minus 5 ln Q equals to 0. Okay, then the next step is to solve for Q. Okay, I will transpose this to the side and I will have minus 5 ln Q equals 25. Okay, then the next step, I divide this by minus 5. If I do that, I will have ln Q equals 25 over minus 5. And this gives me minus 5. Because it's 25 over 5. And this should give us minus 5. But I'm not looking for ln Q. And here we have ln Q equals to minus 5. To cancel out ln Q, we should introduce E on both sides, right? If we introduce E on both sides, we'll have Q E ln equals to E minus 5, right? And this is equals to 1, right? So this means we have Q equals E minus 5, which is, just a second. I feel like, oh, this, if you transpose it this side, this will give you minus 25. So we have minus 25 over 5. That is plus 5. So this means we have plus here, we have plus here, and this is plus. And if you punch this in your calculator, you should get 148,41. And this you can round off it to 148 units. Okay, so this means at turning point, you have 148 units, right? So this means your total revenue has a turning point when the quantity is 148 units. Okay, then the next step is to find the nature of this turning point. We need to determine whether this turning point is a maximum turning point or a minimum turning point, because we need to know whether at this point 148 is the total revenue at maximum or minimum. Okay, so remember, to determine the nature of the turning point, you need to find the second derivative of the total revenue at that point, right? So that simply means we need to differentiate the marginal revenue, because the marginal revenue is the derivative of the total revenue. Remember, to get to the second derivative, we need to differentiate. It's like differentiating the first derivative. Okay, so this means the total revenue the second derivative of the total revenue is the derivative of the marginal revenue. And the marginal revenue is 25 minus 5 ln Q. Where is here is the marginal revenue. And if we differentiate this, you'll have d over dq of 25 minus 5d over dq of ln Q, right? Okay, if we differentiate 25 is a constant. We know from the rules that the derivative of a constant is 0, right? And the derivative of ln Q is 1 over Q. So this means we have minus 5 over Q. We have minus 5 over Q, right? Okay. For all Q greater than 0, total revenue is an increasing function, right? Remember, if the second derivative of the total revenue is less than 0, this implies that we have a maximum point, right? We have the maximum point if the second derivative is less than 0. Okay, and our Q is 148. So this means we have T prime of 148. So this means we have minus 5 of 148, and this is less than 0. The answer here, if you punch this in your calculator, will be less than 0, right? So since the second derivative of 148 is less than 0, we conclude from here that if we produce and sell the 148 units, will have the maximum point, will have the maximum total revenue. Now, what is the corresponding value that will have at maximum? What is the maximum total revenue? So you take this value and put it back to your total revenue function. So we have total revenue of 148, and that is 30 times 148 minus 5 148 ln of 148. And this, okay, this is 30 times 148 minus 5 times 148 ln times 148. If you punch this in your calculator, you should obtain 742. This is what you should obtain, right? Okay. In your spare time, please try and do this example. The outputs, okay, the output over time for a firm is given by Q of T equals TQ over 3 minus 3T squared plus 5T plus 50. Okay, here T is given in years and Q is the outputs in hundreds of units produced. Okay, we need to determine the years when output is at maximum and when it's at minimum. That is the turning point of Q. Okay, you need to find the turning point of Q and determine whether that Q is at maximum or Q is at minimum. Right? Remember, to determine the values of Q at the turning point, you need to differentiate Q. Then you equate it to 0. Then you solve for Q when the derivative is equal to 0, right? And then you to find the nature of those Q, you should differentiate, find the second derivative, and then substitute that value with Q. Okay. But for me, this is what I obtained when I was doing this question. I find 2Q, T equals 1, and T equals 5, right? At T equals 1, at T equals 1, it was less than 0. And at T equals 5, it was greater than 0. Then this, since it was less than 0, it was the maximum point. And T equals 5, since it was greater than 0, then it was the minimum turning point. Yes, but please try and do and solve this equation, this question. Hence, this is what I obtained. I hope you get the same thing. Okay, let's move on to another session, last session on the application of derivatives. Okay, this is the elasticity of demand. Or nonlinear demand function. Okay, in the previous session, which is session 2.3, the section that you did with Prof. Mabemadis, okay, she introduced the concepts of elasticity as okay, the concept of elasticity for linear demand function. Please do go back to it and just to recap, remind yourself. She did introduce it there, okay? And again, the elasticity of demand sometimes is called the demand elasticity, okay? This is just the measure of how demand responds to a change in price or income. Okay, price elasticity is important influence because it influences the price the firm will charge for products or service. So it helps the business, like it helps the firm decide how much are they going to charge on their products, right? And in addition, it helps business develop strategies, maximize profits, and reduce risk. So for them to maximize their profits and reduce risk, they need to know the elasticity of demand. Yes. Okay, suppose you are given a demand function as E equals to A minus B Q. Okay, suppose you are given the demand function as this. To calculate the elasticity of the point elasticity of demand for this linear function, you will have This is what you'll use. Elasticity, the point elasticity of demand will equal to the change in Q over the change in P times P over Q, right? The change in Q, the change in Q over the change in P times P over Q. And this is the same as minus 1 over B times P over Q. This is the same thing. So this simply means to find the point elasticity of demand, if you are given this linear function, this is what you'll use. Minus 1 over B times P over Q. That's how you'll find the point elasticity of demand. Then, okay, here you were given a linear function. If, again, you are given a nonlinear function, nonlinear demand function, then this is what you'll use. You'll use the derivative. You'll have point elasticity of demand as dq over dp times p over q. Remember, this is the derivative. So if you are given a linear function like this, this is what you'll use. But if you are given a nonlinear function, this is what you'll use. You'll use the derivative of q with respect to p times p over q. Okay, please do not confuse these two. Okay, and again, another thing that you need to know is that the derivative of a demand function is given by either dp over dq or dq over dp. It depends on the format of the function. If your function is given in terms of p, then your derivative would be dp over dq. If your function is given in a form of q, then your derivative, then your function, I'm sorry about that, then your function would be given as dq over dp, as in you differentiate the q function with respect to p. If your function is given in terms you'll have this. If your function is given as p, you'll have this derivative, the derivative of p with respect to q. If your function is given in terms of q, you'll have the derivative of q with respect to p. Okay. Another thing, dq, the derivative of dq with respect to p is just the inverse of the derivative of p with respect to q. Okay, so this means dq over dp is equal to 1 over dp over dq. Okay. Then we have the conditions, 4 conditions of elasticity. Okay, here, these are the conditions you need to know. Or conditions for elasticity. Okay, if the absolute value or the point elasticity. If this is greater than 1, then you'll say for a certain price, the demand is elasticity at that price, right? Meaning that if the price increased by 1%, the demand decreased by more than 1%. So if this is what you obtained, if it's greater than 1, then this means the demand is elastic. Demand is elastic. Okay, and if the demand is elastic, this means if the price increases by 1%, the demand decreases by more than 1%. Okay, then we have another condition. If the absolute value of the elasticity of demand is less than 0, then here we say the demand is inelastic. Inelastic at that price, at that given price. And this simply means if the price increases by 1%, the demand decreases by more than 1%. Okay, then we have last condition, which is equals to 1. If this is equal to 1, this is inconclusive. We have an entire elasticity. And this means when the price increases by 1%, demand decreases by 1%. Okay, here on the first one, this means the demand is elastic. Ne? And this means if the price increases by 1%, the demand decreases by more than 1%. Here, the demand is inelastic. This means if the price increases by 1%, then the demand decreases by less than 1%. Okay, and then here, if the price increases by 1%, then also the demand decreases by 1%. Okay, let's try and do an example to put this in practice. Example. Consider a demand function as P equals to 100 minus Q squared, right? Okay, here our demand function is given in terms of P, right? So this means our derivative will be dP over dQ, which is minus 2Q, right? Okay, since for a demand for a point quantity, this is the formula we use. EQ equals dQ over dP times P over Q. Okay, since it's this, but the function is given in this form, and this is the derivative we obtain. But we said dQ over dP is equal to 1 over dP over dQ, right? So this means here we have this. Okay, if this is this means dQ over dP would be 1 over minus 2Q, right? So this means we have 1 over minus 2Q times P over Q, right? But we know that we know that we know that P is equal to 100 minus Q squared. So this means we have 1 over minus 2Q times 100 minus Q squared, right? And this is Q. So where there is P, this is what I substituted P with. And this will give us 100 minus Q squared over minus 2Q squared. This is our point quantity of demand. Right, this is our point quantity of demand. Now, suppose that we are given the price as 50 per unit. We have price as 50 per unit. So we have P equals 50. Right. What is Q if your P equals, what is your Q if the price equals 50? So you can just come here where there is P and substitute. Okay. You are told that P is equal to 100 minus Q squared. And this is 50. So we have 50 equals 100 minus Q squared, right? If you solve for Q here, you'll have Q squared equals 100 minus 50. And this is 50, right? And then if you square on both sides, you will have something like this. Okay. Right. You will have Q equals 100 minus P, but your P is equal to 50. So this means you have a square root of 50. Then you can punch this in your calculator. If you punch this in your calculator, you should obtain 7,01. Right. Then the next step is to take that Q and substitute it here. So, okay. Q squared is, no, Q is equal to square root of 50, right? Square root of 50, Q. So if Q is equal to square root of 50, that means Q squared is equal to 50. So let's come here and substitute the value of Q squared, which is 50. So this means we'll have the point elasticity as 50 over, okay, it's 100 minus 50. Okay, so 100 minus 50 over minus 2 times 50. And this is 50 over minus 100, and this is minus 0.5. And the absolute value of the point elasticity is equal to 0.5. 0.5. This is equal to 0.5. Since 0.5 is less than 1, then you go back to your condition and check if this is elastic or inelastic. Go back to your conditions. Remember, I said if the absolute value of the point elasticity is less than 1, then you say the demand is inelastic. So this simply means if we are given this data and this is what we obtained, the absolute value of the elasticity of demand is 0.5. Since this is less than 1, then we say the demand is inelastic at this price of 50, because we said the price is 50. We were given the price as 50. And then that simply means if the price increases by 1%, the demand decreases by 1%. Again, then we should stop here until our next session. Okay. Monday we have tutorial sessions based on the two videos that I've recorded on my own. Okay, let me stop recording.